Welcome, Hornets. In this video, we're going to be taking a quick look at Rolle's theorem. Rolle's theorem is a very straightforward theorem that tells me that if I have two values, f of a equaling p and f of b equaling p, if I know that I have a continuous and smooth curve from a to b, which once again is continuous and smooth and therefore differentiable, there has to be at least one place in the graph that has a parallel line to the slope of the secant line between them. So this secant line right here has an average rate of change, f of b minus f of a over b minus a. And we know that it has a slope of 0 since p is f of a and p is f of b, and p minus p is 0. So if I'm looking at a situation and I see two y values that are equal at two different x values, the secant line between those 2 points has to have a slope of 0. And if I have a function that is both continuous and smooth, then there must be at least one critical value on that interval. One place where the derivative is going to equal 0. And this is what Rolle's theorem tells us, that there has to be at least one place on this closed interval where we will have a derivative that is equal to 0 if the secant line between two endpoints is 0. Now, the mean value theorem was the next step. Rolle's and a lot of his colleagues at that time said, this is fantastic. We have to have critical values on this interval a to b. But what if we tilt the curve? What if we take a look at two values that are unequal? Well, once again, we're still looking at the slope of a secant line called the average rate of change. So if this is f of a equaling p, and this is f of b equaling q, then there has to be an f of b minus f of a divided by b minus a. And it has to equal a derivative at some other value on this interval. And you'll notice if we just draw our parallel lines, we have one here, and one here. And they're happening everywhere we have an extrema, equivalent extrema. Okay, that's what's happening. It's an equivalent extrema. We tilted it and rotated it. They would then be critical values where the slopes are 0. But what we're now saying is that the slopes aren't 0, they're equal to the average rate of change. And this is something that I've been asking you to do quite frequently. We started off by saying, here's a derivative. When is the derivative equal to this amount? And then I said, here are two derivatives. When are they equal? And then I said, what is the average rate of change for this function? What is the derivative for the function? And when is the function equal to the average rate of change? Now we're identifying that as satisfying the mean value theorem. And the last thing I need you to do is recognize that Rolle's and the mean value theorem, just like IVT, have a set bit of information. If I know that there is a derivative or a slope of a secant line, f of a, minus f of b over a minus b, and it has a slope m, then there must be a derivative on the interval a to b, now it's open, such that the derivative will equal that slope. So when we are asked If this occurs and the function is continuous and differentiable, MVT applies. So we would say yes by MVT because f of x or f of t or whatever it is continuous on the closed interval a to b and differentiable on the open interval a to b, and there is a secant with a slope of m. And I would then write that secant down. F of a minus f of b over a minus b equaling whatever it is, equaling m. And this is our justification for MVT. If we were using Rolle's theorem, we would say yes by Rolle's theorem because f of a equals f of b, and f of x is continuous on a to b, and differentiable on an open interval a to b, and there's a secant line with a slope of 0. Okay, and then I would just go through and I would show f of a minus f of b equaling p minus p over a minus b equaling 0 over something. So this is MVT and Rolle's theorem. They are fairly straightforward. They are talking about slopes and when is a derivative equal to that slope. Our first situation was dealing with Rolle's theorem. And if we have a secant line with a slope of 0, then there must be a critical value on that interval, a to b, such that the derivative is equal to 0. And then we had MVT, which takes it as a slanting line. Please be aware you can always use MVT instead of Rolle's theorem. It is still applying. But you cannot use Rolle's theorem for slanting lines. All righty. Thank you very much, Hornets. I hope this was useful to you today, and we will continue working on this all week. Be well, be safe, and take care. Good night.